Howdy. In this lesson, we're going to be talking about finding the lift and drag over an entire airfoil given an elliptic lift distribution. So in the previous lesson, we started with this elliptic lift distribution, where gamma naught is multiplied by the equation for an ellipse. And we found that the downwash was constant, which means that also the induced angle of attack is constant. Now, whenever we're finding the lift per unit span, we know that this is simply the density times the velocity times our circulation. This just comes from the basic idea of circulation creating lift. And then based on the induced angle of attack, we also have a drag per unit span, which is simply equal to the lift per unit span times sine of the induced alpha, or the induced angle of attack. But because we're assuming small angle, we just multiply it by the alpha I. So let's go ahead and integrate our lift per unit span over the entire span of the airfoil. So the entire lift is going to be the integral from negative b over 2 to b over 2 of the lift per unit span, which in turn, after taking out the constants in front of the integral, we end up with this rho v times gamma naught times the integral from negative b over 2 to b over 2 of this elliptic distribution. And that is all integrated over dy. So the next step here is to use the same substitution where y is going to be equal to negative b over 2 times cosine of theta, and dy is going to be equal to b over 2 times sine of theta. So we can plug this in, and we arrive at rho v infinity times gamma naught, and then this substitution yields a b over 2. And then we integrate from 0 to pi of the square root of 1 minus cosine squared theta times sine theta d theta. So once we actually perform this integration, this becomes a square root of sine squared times the sine. And so this entire thing is the integral from 0 to pi of sine squared d theta, which is simply equal to pi over 2. So this the entire lift can be written just as rho times v infinity times gamma naught times b times pi times 1 over 4. Okay, but normally we're interested in looking at the coefficient of lift. So the CL is simply equal to lift over 1/2 rho v infinity squared times s. So this is going to be rho times v infinity times gamma naught b pi all over 4 times 1/2 times rho v infinity squared times s. So the rho, this top v infinity go away, and we're left with a gamma naught b times pi all over 2 v infinity s. Well, as you might imagine, since the drag per unit span is simply equal to the lift per unit span times this constant alpha sub I, then this means that our induced drag is going to be equal to the integral from negative b over 2 to b over 2 times the lift per unit span times our alpha sub I dy. Well, we already know that this is a constant, so we can just bring it out. So this is simply going to be equal to rho times v infinity gamma naught b pi times alpha I over 4. Well, really that's a lot more than we want to say, so we're just going to say that this is lift times alpha sub I. So whenever we non-dimensionalize this and look for CD sub I, then this just becomes our CL times our induced angle of attack. Okay, so now let's go ahead and substitute out our induced angle of attack and try to get this in terms that make a little more sense, that have a little more meaning in comparison to the rest of our units. Okay, so if we substitute out and isolate gamma naught here, then we can say that gamma naught is going to be equal to 2 times v infinity times s, all that times CL, all over b times pi. And we know that alpha sub I is going to be equal to gamma naught over 2b v infinity, which is going to be equal to all of this divided by 2 times b times v infinity. So this is going to be s times CL all over b squared pi. All right, so now we can write this in very simple terms, and this will be CL squared times s all over pi times b squared. Well, this term here has a special meaning, and it's known as the aspect ratio, which is simply a measure of how long the wing is. So the higher the aspect ratio, the longer b is compared to the total span, or compared to the total surface area. Regardless, we can write this as CL squared over pi times the aspect ratio. And this is our induced drag in terms of the coefficient of lift.